to the class. Dear students, today we are going to see cycloalkanes, the method of preparation of cycloalkanes. So we will have a small discussion on what are cycloalkanes, and we are going to see the 4 methods of preparation of cycloalkane. So let us start the class. Cycloalkanes. So cycloalkanes, what are they? They are saturated hydrocarbons. They are saturated hydrocarbons, the terminal carbon atoms of which are joined by single covalent bonds as to form a ring. So what did I say? What are cycloalkanes? They are saturated hydrocarbons, the terminal carbon atoms of which are joined by single covalent bond so as to form a ring. Such compounds are called as cycloalkanes, or you can just simply say that they are alkanes in which the terminal carbon atoms are joined by single covalent bond as to form a ring, referred to as cycloalkanes. So they are actually alicyclic compounds. What are they? Alicyclic compounds. So the word alicyclic is made up of 2 things. This is aliphatic, the other is cyclic. So that is the definition, right? It's an aliphatic compound that is cyclic. So that is why it is called as alicyclic compound. Now the main difference, one of the differences between alkane and cycloalkane is its general formula. The cycloalkane's general formula is CnH2n, and the alkanes, its homologous alkanes the general formula is CnH2n plus 2. So as you can see, there are 2 hydrogen atoms less in cycloalkane. And why these 2 hydrogen atoms are less? That is because the terminal carbon atoms have joined to each other through single bond, eliminating 2 hydrogen. That is why 2 hydrogen atoms are less in cycloalkane. That is why this general formula is CnH2n. Exactly how these 2 hydrogen atoms are eliminated, we will see in preparations. Okay, various methods of preparations. So let us start preparations. The first method of preparation is for smaller cycloalkanes. It is for smaller cycloalkanes. When I say smaller cycloalkanes, what I mean is cyclopropane and cyclobutane. Only these 2. Okay. So we prepare cyclopropane and cyclobutane through this method, which I am going to show you now. It is from dihaloalkanes. Let us see this method, how we can make from dihaloalkane. So for this, let me prepare the smallest of all cycloalkane, which is cyclopropane. For that, I take this compound. This is 1,3-dichloro-propane, right? 1,3-dichloro-propane, correct? Now let me react it with sodium, 2 sodium, and let me heat it here, okay, in the presence of dry ether or ethanol. Let me put ethanol here, okay. Dry ether you can take. What happens here? It is very simple. This 2 chlorine, it would go with sodium, and these would get connected, CH2, cyclopropane, and 2 NaCl. I hope you got it. It's so simple, right? Just take out these 2 chlorine and connect it with sodium. Let us see another example to make our cyclobutane. For that, I take 1,4-dichlorobutane, and I heat it with sodium. Either you take dry ether or you take ethanol and heat it. I am taking here dry ether. Just heat it, take out these 2 chlorines and combine with sodium and put a single bond here. You get cyclobutane. Fine. Ain't it simple? Yes. So this is the method of preparation for smaller cycloalkanes. So at first glance it seems very simple, but how this mechanism works, Let us look into it, how this mechanism works. For this, let me rub this one and let us see that in the first example how actually it works out. Fine. So when, see, you are, for understanding this reaction, for a better understanding of this reaction, you need to know the atomic number of sodium. What is the atomic number of sodium? Yes, 11. What is the configuration? 1s2, 2s2, 2p6, 3s1. Am I right? And what is the atomic number of chlorine? 17. Can you say its electronic configuration? Yes, 1s2, 2s2, 2p6, 3s2, 3p5. Right? So as it, you can see, as is obvious, that sodium needs to lose this electron to get a octet configuration in the second orbit, to get a stable configuration. And as is obvious, chlorine needs to get one electron here so that octet configuration is obtained in the third orbit. So there is a need for sodium to lose electron and there is a need for chlorine to gain electron. And this heat does the same. When we heat it, what happens? This electron here, it goes and jumps into the third orbit of the chlorine atom. Correct? In this process, in the process of losing, Na becomes positive, and in the process of gaining, Cl becomes negative. And now what happens? The nucleus of this sodium attracts the electrons of this chlorine and they come close to each other. So the chlorine comes close to each other and they form ionic bond. Correct? The chlorine prefers to have ionic bond because ionic bond is much stable than a covalent bond with CH2. Okay, therefore the chlorine would prefer to have ionic bond because in the ionic bond the electron is actually in the orbit of chlorine. In covalent bond it is not the same case, it is being shared. Okay, but in ionic bond the electron is actually in the orbit of chlorine, so chlorine may become more stable and sodium also would become more stable. So an ionic bond is stronger than a covalent bond, it is more stable than a covalent bond, therefore chlorine leaves its association with carbon. When it leaves its association with carbon, it takes its electron. Okay, because covalent bond is made up of two electrons, as you know, it takes only its electron. When it takes its electron, okay, when chlorine takes its electron, the atomic number is 17 only. The configuration is like this when it takes its electron. Right? Okay, and then it gets an electron from sodium. It gets an electron from sodium, right? And that makes chlorine negative and that makes sodium positive, and that is how they come close to each other, right? And that is how they form ionic bond. Okay, so what I want to show you is that it takes its electron but it leaves one electron. It leaves one electron, that is, it leaves the electron of CH2 here itself. It doesn't take that electron. Okay, now what these carbon atoms do, they share their unpaired electron and that results in covalent bond formation, and that is how your cyclopropane is formed. That is how cyclopropane is formed. So this is the actual process behind it. So you can say the mechanism of this is a free radical mechanism where free radicals are formed and then it combines, right? So this is an extension. One more point that I want to put here is this reaction is an extension of Wirth's reaction. What happens in Wirth's reaction is we prepare alkane through alkyl halide. Same thing is going on there also. We use dry ether or ethanol, and what happens? This takes place. Sorry for this. Sodium eliminates the two XX halogen atoms from here, and that results in R free radical and R free radical, and they go for covalent bond formation, and 2NaX results. Ionic bond formation results. So here we are seeing that sodium in Wirtz reaction, when in the presence of diethyl ether, when it is heated, sodium in Wirtz reaction eliminates halogen from two different molecules. It eliminates halogen from two different molecules. But here in this reaction, in the preparation of cycloalkane, we have seen that sodium eliminates chlorine from the same molecule, or from the same, yes, from the same molecule. So this is elimination internally. Right? This is an internal elimination. So therefore this reaction is called as internal Wirtz reaction. What is it called as? Internal Wirtz reaction. Internal Wirtz reaction. Right? So these are the points related to this reaction. Okay, now this is for smaller cycloalkanes. Let us now go for higher cycloalkanes. So this is the second method of preparation, and the most important of all. When I say higher cycloalkanes, what I mean to say is above a cyclopentane and above cyclopentane. Okay, so there is a reaction called as the Dickman reaction. Dickman reaction. Dickman reaction. This reaction is used for preparation of cyclopentane and other higher cycloalkanes. Let us see how this reaction is coming. So for this we are taking diethyl adipate. Diethyl adipate. For this, let us know what is adipic acid first. This is adipic acid. This is adipic acid. We know all these are related: oxalic acid, succinic acid, malonic acid, and adipic acid. All these are higher analog. First oxalic comes, then malonic comes, then succinic comes. In this way, this is adipic acid. Okay. Now let us draw diethyl ester of adipic acid. So you need to do like this: diethyl ester of adipic acid. This is the diethyl ester of adipic acid. Okay, now let me remove this. Okay, let me rewrite it in another format so that we can understand the mechanism. I draw it like this. Okay, and let me rub this also. Okay, let me draw H here. This is CH2, and let me draw it downstairs so that we can better understand the mechanism. Let us heat it with sodium. Okay, let's heat it with sodium. So what happens here in Dickman reaction? This is the first step. This is diethyl adipate. Diethyl adipate. Adipate. Okay, what happens in this step is when we heat, electron is kicked out of sodium. Electron is kicked out of sodium. And when electron goes out of sodium, sodium actually loses an electron, it becomes positive. Okay, and this heat simultaneously, there is problem here, there is a polarity here. This carbon is positive and this electronegative oxygen is negative. This is a polar covalent bond. Here also polarity exists, correct? So there is actual very strained, these bonds are very strained. It is easier to break this bond than to break this, because single bond has having lesser energy and heat is also applied. So obviously this bond will be broken either from this side or from this side. Okay, so this bond, when it breaks, it results in O minus C2H5 that combines with sodium. Okay, and that results in C2H5 ONA. O minus Na positive. Okay, so that results in this compound. Okay, let me rub this one. I hope you understood how C2H5ONA comes. Okay, so I am rubbing this one. There is electron here, correct? So when it goes, this carbon becomes positive. This carbon becomes positive. So what it does is it pulls this electron pair towards itself. The positive charge of this carbon pulls the electron pair towards itself. That results in H plus. H plus is eliminated out. Okay, and this sides, they get joined to each other. These and these sides get joined to each other. And what H does? H plus accepts the electron and become H atom. Okay. When in another molecule cyclization occurs like this, another H plus is released. It would combine with another E minus to form H, free radical. Both these H then combine together to form H2. Fine. So its fate is also decided, right? So now we get the compound. What compound we get? Let us write the compound. So as we said, C2H5O minus Na plus goes out when we react it with sodium, heat it with sodium, right? I can write it here itself, right? That goes out, and what results? These two sides join and they form a cyclic structure, right? And how these two rings are joining we have shown. Now we got like this, correct? So this is our first step. Let me rub this one now. Okay. Now what is done in the second step? We go for dilute HCl. Dilute HCl. What would happen if I am putting dilute HCl? Let me rub this and put a bond and write C2H5. No issues. Okay. And let me show the lone pair of electrons on oxygen. Fine. Now what happens if I put dilute HCl? See, HCl plus water. That is what is dilute HCl. It has lone pair. H plus would come out. Structure of water is like this. Correct? H plus would come out of this, and that H plus, it would take a lone pair of oxygen. Because oxygen has donated its lone pair to hydrogen, this would become positive. Now what would happen? This is very unstable condition. Am I right? So oxygen tries to take this electron back and H plus goes out. So the net result is that H plus goes out. Fine. So there is H plus generation here. What this H plus does? It combines with oxygen. Now there are two oxygen atoms here. This oxygen atom is also have lone pair of electron. This oxygen atom also has lone pair of electron. Which oxygen atom it would attack? Definitely it will attack this oxygen atom, because pumping group is present here. So it will pump its electron, and the availability of the electron is more here. The availability of the lone pair of electron is more here. So H would combine with this oxygen. So let us combine and see. Let us combine and see H here. Okay. Now H, when it combines with this oxygen, because this oxygen has lost its lone pair, this oxygen would become positive. The oxygen would want to have electron back into its system. So it pulls this pair of electron, it would pull towards itself. So when it pulls, it becomes what? It becomes C2H5OH. C2H5OH. So that is what comes out. So because electron pair was taken, this becomes positive. This side becomes positive. Correct? So what was formed from this? I rubbed it. Look at this. This was the reaction we wrote, right? This was initially what was formed here between these two, and then it split into H2O and H plus. This is what we wrote. Yes. So now our solute is actually positive. It would have a drastic effect on water. Okay. Water is aprotic in nature. Water is made up of H and OH. So when water comes in contact, it polarizes and it splits into H plus and OH minus. The OH minus of the water component, the OH minus component of water, it goes and attaches to this. Okay. So we get a product. For second step, what do we get? Yes, let us write it. So we get, yes, that is what happens here. OH comes and attaches to this. Okay, OH has come from water and water has come from dilute HCl. Okay, so that is how OH comes and attaches to this structure. So we got this compound. Now look at this compound. We have seen this earlier also. This is beta keto acid. See, this is the acid, this is functional group. Alpha carbon atom is this one because this is the functional group. Which is the beta carbon atom? This is the beta carbon atom. So it is a beta keto acid. So beta keto acids have a distinguishing feature. That feature is that when you heat it in acidic condition, it will lead to decarboxylation. That would lead to decarboxylation. Let us understand decarboxylation. Okay, let us understand decarboxylation. Let me write it as COOH. So when you are heating it, okay, in acidic condition, what happens here is that this H plus it would go. Okay, this H plus it would go and it comes here. This electron pair it would jump on oxygen. Okay, so oxygen would become negative. Okay, and now this oxygen would come and become a covalent bond with carbon. When this occurs, carbon valency will become 4. So this would be split. This portion of the molecule will split and that molecule, this would become CO2. It would become CO2. So when this molecule, this CO2 is split, this electron pair is left, right? So this side becomes negative. This CH becomes negative. To this negative CH, H goes and attaches. And what results? It becomes CH2. It becomes CH2. So that is the product of the third step. A cyclic ketone is formed. A cyclic ketone is formed. Now what we can do is, this is a ketone. We can convert a ketone into alkane. There is a reaction called as Clemmensen reduction. In Clemmensen reduction we are using for zinc amalgam in the presence of HCl. So when we treat it with zinc amalgam in presence of HCl, then for that this ketone group should be stable in acidic condition. Only those ketones that are stable in acidic condition will undergo Clemmensen reduction to form alkane. So that results in alkane like this. I am rubbing this 2H and I am writing it as CH2. This is our cycloalkane, the simplest, the smallest of higher cycloalkane, which is cyclopentane. Cyclopentane. To understand Clemmensen reduction, this class would not be enough and this video would become very long. So I will take Clemmensen reduction in another session. So this is what happens here. In Clemmensen reduction, the priority is that the determining factor is that the ketone should be stable in acidic condition. And in Clemmensen reduction, the ketone is reduced into alkane. So it is carried out in zinc amalgam in HCl and here we get a cyclopentane. Okay, we will cover Clemmensen reduction in another session. This video would become too lengthy if I cover Clemmensen reduction. So that is the Dickman reaction. I hope you understand Dickman reaction, which is a very important reaction. Now, which is the third method? The third method is you can prepare cycloalkane from aromatic compounds. So I take the prototype of aromatic compound, which is benzene. Okay, benzene is the prototype of aromatic compound. Fine. And I treat it with 3H2 so that there are 6 hydrogens are added, nickel, and heat it. And what you get is simply cycloalkane. Okay. It is actually put some pressure also. Okay. Fine. It is actually very easy to hydrogenate benzene because the heat of hydrogenation of benzene is 55 kilocalorie per mole. 55 kilocalorie per mole. That much energy is needed to hydrogenate benzene. Okay, if benzene didn't have resonance, Okay, if benzene actually has resonance, that is why only 55 kilocalorie per mole of energy is needed. If it was the case that benzene doesn't have resonance, if the double bonds of the benzene were static, then it would have been 85.8 kilocalorie per mole would have been required. If benzene would not have resonance, if there was no resonance in benzene ring, if the double bonds were static, then this much energy was required for hydrogenation. But because it is having resonance, benzene is having resonance, benzene is thermodynamically stable, only 55 kilocalorie per mole of energy is required. The subtraction of the two, that is 35.8 kilocalorie, that is the actual resonance stabilization energy of benzene. Resonance stabilization energy of benzene. To understand what is resonance in benzene, please do refer to my video class resonance, where I have discussed this heat of hydrogenation of benzene and proved that resonance actually exists in benzene. So what we need to know here in this section is that there is this method from which you can make cycloalkane and its derivatives from aromatic compounds. Okay, now let us go for the fourth method of preparation of cycloalkanes, that is from calcium and barium salts of dicarboxylic acids. From calcium and barium salts of dicarboxylic acids, let us see what it is. So for this I take adipic acid. This is adipic acid. I take the barium salt of adipic acid. I heat it. So when I heat it, what happens is CO2 goes from here. This is oxygen, right? No problem if I write like this, correct? What would happen here when I heat it? See, this bond is actually very polar. This is electropositive in nature and this is very electronegative in nature. So already there is a tension here. Here also there is a tension. So any of these bonds can break. So this actually breaks. But when it breaks, it takes the electron pair towards itself. And this electron pair jumps here. When it jumps here, carbon valency is completed. It becomes 4. So it splits from this portion and it becomes a CO2, right? And an electron pair here is left. An electron pair is left here. Here also what happens? This is CO, fine. Here also what happens? OB, this portion, it gets split and it becomes BaO minus. That is what happens here. Okay, and why it splits from here? Because it is barium has become positive, correct? When CO2 was taken from here, it split from here, it took the electron pair, so barium became positive. So now the positively charged nucleus of barium tries to put strain on oxygen. Okay, this bond is also strained, plus this bond is also strained. So that is why BaO minus is split up from this section and it goes as BaO minus. Carbon dioxide has got a resonating structure. As you know, it can exist in any of these two forms, or it can exist like this. In both these forms, carbon becomes positive. Here also it becomes positive. So in these two forms, it can exist, carbon dioxide. The positively charged carbon now attaches to oxygen and it would become what? BaCO3. So that is how BaCO3 results. So BaCO3 comes out. Here when it was taken, it becomes positive and this side is negative. So what is the net output? Yes, let me rub this. The net output is CH2, 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 a cyclic ketone. Now as discussed earlier, we have got a cyclic ketone and this is actually stable in acidic condition. So we can use Clemmensen reduction to go for its reduction to cycloalkane. Go for Clemmensen reduction, take zinc amalgam, HCl, and what you get is a cycloalkane like this. Dear students, I hope you have liked and understood the class. If you have done so, please do not forget to subscribe the channel. Please do share it and please do like it. Thank you very much.